age of the universe.
What a beautiful sight. I wonder, has it always looked like this? A few of these millions of stars could move without my noticing it, but what about the Big Dipper, whose shape is so familiar? Could it ever, long ago, have looked like a shallow pan? Or, to go one step farther, have the 7 stars of the Dipper always been there? Do some stars fade out and die? And do others come up to replace them?
Our topic is the age of the universe. Perhaps it would have been a little more modest to speak in terms of the cosmic time, because what we shall be doing is to consider changes that are taking place in the universe and try to see how fast these changes are taking place. In other words, is the universe as we see it now, the solar system, the Milky Way system, the stars in the system, has that always been the same as it is now? The answer to that question is no. It must have been changing. Let's ask another question. If it has changed, can we roughly say how fast these changes are taking place? The answer to that question is yes. We can, in many cases, pin a very definite time scale of development to our cosmical phenomena. So what we're going to do is to talk about the time scale of development. Let us start with a simple reference point. Because our times are going to be rather large ones, we must pick some fairly definite units and get these firmly fixed in our mind. The first one that I shall want to consider is that of the age of our own Earth. Our own Earth has an age of approximately 5 billion years. So, age of Earth equal to 5 billion, that is 9 zeros, of our regular years. That age has been determined by geologists, and the geologists have been helped by the physicists. They have done it by radioactive techniques, finding out how long it takes for rocks to change their composition, how many of the decay products there are around, and in that fashion it has been possible to find a pretty good figure for the age of Earth. 5 billion years is that figure. Now let's go out in the universe. Start looking at our own Milky Way system and begin with one of the photographs of a region of our Milky Way system in the constellation of Cygnus. Probably many of you know this part of the sky. It is not far from bright Deneb, the northern cross. And there on this photograph we see the dots which mark the stars. We see the clouds of gas, here this famous North American nebula, shaped purely by accident in the shape of the continent of North America. That's a cloud of gas floating in between the stars. Therefore, we have our matter partly in space in these clouds of gas. Part of it is also in the stars. Roughly speaking, for every 3 grams of matter that we have in space, there are 2 grams squeezed into the stars, like our own sun and others, and there is 1 gram floating in between the stars in these clouds here. In addition to the interstellar gas, there is the cosmic dust. Look, for example, here at the Gulf of Mexico of our North American nebula. See how dark everything looks there. Why is that so? Because there is overlying this region a large cloud of opaque cosmic material. Tiny little icicles that screen off the light from the stars that lie beyond. Cosmic dust, cosmic gas, and stars. That is what our universe is made of. Our own Milky Way system, of which this cloud is just one example, is a vast system in which the stars, the gas, and the dust are intermixed in about the same proportion that we had here. Here is a drawing of a large-scale map of our Milky Way. Every one of these clouds that you see here is really a composition of a great many stars, so many close together that they make the appearance of a star cloud. The stars are more numerous along the band at the Milky Way than at some distance away from it. In the Milky Way, they're not distributed in a perfectly regular fashion. In some parts, they are very much denser, like, for example, the Milky Way of our summer, of Sagittarius and Scorpio. In other parts, like the Milky Way of winter, of Taurus, and of Orion, there one finds much thinner part of the Milky Way. What is the place of our sun in the Milky Way system? And what roughly are the dimensions of that Milky Way system? This drawing here shows this rather clearly. Let us turn first to the one on the right. In the one on the right, one has a view of our Milky Way system of stars, as viewed from a great distance above it, a couple of million light years or so. As one looks at the Milky Way, one sees that it is a flattened system in the shape of a wheel or of a watch, one might even say of a pancake, because it is quite thin. And our sun is just an average star, neither very bright nor very faint, in the outer part of the system. At the speed of light, which is 7 times around the Earth in 1 second, this is a scale of 100,000 light years. In other words, the diameter of the system is approximately 100,000 of these light years. The distance from the sun to the center of our galaxy is roughly, because we use these terms Milky Way system and galaxy intermingled, the distance from the sun to the center of our galaxy is approximately 27,000 of these light years. Seen edgewise, the system would have this appearance. It would appear like a flattened system with a central bulge very clearly marked. Again, with the sun located in the outer part, 27,000 light years from the center. If we could go a long distance away from our Milky Way system and look back at it, it would probably appear something like this spiral galaxy or spiral nebula, as we sometimes call them. If this were our system, from here to there would measure just about 100,000 light years. Our sun's position would be marked by this little black arrow here, and from here to there would be 27,000 light years. The Milky Way is highly flattened. It is really a thin, flattened system. It is probably in rotation around its center. And we ask how fast it goes. Well, from the sun to the center, 27,000 light years, our sun moves at a rate of approximately 140 miles per second in a direction something like this here. How long does it take the sun to go once around the center? For that is a useful time to keep in mind. Can you see it? Here is the sun, here is the center, 27,000 light years, 140 miles each second. The sun and the Earth comes along with it. How long does it take to go once around the center? That interval, which we shall call the cosmic year, is equal to roughly 200 million of our regular years. Now, if you would keep this in mind as our second basic feature, that our sun moves once around the center of the Milky Way system in 200 million years, we shall call this one cosmic year. So I return to the blackboard, and we write there that one cosmic year is 200 million regular years. 200 million, a 2 with 8 zeros, regular years. Now we can begin to write the age of the Earth in a slightly different fashion. It was equal to 5 billion cosmic years, and you see 5 billion regular years. That is 25 of the cosmic years. So, roughly speaking, since the beginning of our Earth, the sun has moved approximately 25 times around the center of the galaxy. That is why we say that the age of the galaxy is 25 cosmic years. What sort of changes do take place in a period of the order of 25 cosmic years? Well, this diagram gives a rather nice sample of the sort of changes that take place inside a few cosmic years. Here we have a typical galaxy, an object with a mass and a diameter equal to that to an average Milky Way system. And we have lined up 10 different points, no 11 of them altogether, 11 different points from here to there. Let us assume that this one rotates around its axis, just like our Milky Way system. How will the shape of this line change? Well, as it rotates, the inner parts move faster than the outer ones. So this will be pulled out in a spiral-like feature. And look how beautifully it looks. One revolution later, one cosmic year later. In other words, a very fine spiral will have been produced in that interval of time. Many of the spirals that we see have this sort of appearance. And quite a few look a little more like the case after 2 revolutions, where we will find that things begin to wind up a little bit. The inner parts are winding, turning faster than the outers, and the spiral is really beginning to wind up. After 3 revolutions, we begin to see evidence that the spiral is getting too much wound up for comfort, that it becomes difficult to see the details of the spiral structure any longer. In other words, a spiral feature will probably last for something of the order of 2 or 3 cosmic years, not for 25 cosmic years. And changes must be taking place in our universe in intervals of the order of 3 cosmic years. Now, if we want to find out where these changes are most marked, then we come especially to the groups or the clusters of stars. Let us take the most familiar one of all, the famous Pleiades clusters, the famous group of the 7 sisters. Well, there are more than 7 sisters there, for there are about 400 stars at least in this grouping of stars. These stars will interact with each other as they pass by each other. They will be acted upon by the pull from the different field stars that pass it by. Those field stars may pull more on one star than on another, gradually have a tendency to loosen up the cluster a little bit. The shearing forces of the nucleus of the galaxy will be trying to tear the inner parts around a little faster than the outer parts, which as a result that there will be a tendency to tear the whole cluster to pieces. How long will the Pleiades cluster last? Well, we can calculate it. The Pleiades cluster should disappear from the celestial scene in just about 25 cosmic years. So now you see the Pleiades cluster, wait 25 cosmic years, and gone it will be, it will not be there. We can therefore write on the blackboard, Pleiades cluster out in 25 cosmic years. So the Pleiades out in 25 cosmic years. I shall just write CY, C for cosmic, Y for year. The Pleiades cluster is one of the denser of the clusters of stars that we find in the sky. We ask what will happen to the more rarefied ones. I think all of you may know the second one, or a good many of you anyhow, the so-called Hyades cluster, a V-shaped group of stars tied into the famous bright star Aldebaran. The Hyades cluster has a rate of development that is faster than that of the Pleiades. You can see why. The stars there are pretty far apart, and these arrows here, which indicate the amounts and directions of their motion, are not all of equal size. In other words, in the Hyades cluster, some effects of the passing with field stars have already become noticeable, and we see the cluster slowly running away from each other, without probably enough pull to keep the brethren right at home and keep the cluster tied together. One can calculate what the future is of this cluster. In all probability, it will go to pieces in something like only 10 of these cosmic years. So here is a phenomenon that changes markedly in 10 cosmic years. So the Hyades out in 10 cosmic years. And as you see, things begin to speed up in our cosmic picture. Let us take one other very familiar cluster of stars, the famous group of stars in the Big Dipper. The stars in the Big Dipper, with the exception of the two end stars, this one and that one up there, all the others are moving strictly in parallel paths to each other, which means that they are now running together as a group. But because of the passage of field stars, the tearing effects of the rotation of the galaxy, this will not be a permanent arrangement. This will be a very short-lived affair because it has no gravitational pull of its own to hold it together. 2 to 3 cosmic years should suffice to disintegrate this cluster. So for the group connected with the Dipper group, we find that it will be out in about, say, 3 cosmic years. There are some of the mechanical evidences for development in our universe. Clearly, time intervals of the order of a few cosmic years begin to suffice to give major changes. Let's ask one other question. We have now the Pleiades. If they go out, if the Hyades disappear, are there other groups that will take their place? The answer to that question is probably no. Therefore, change takes place fairly rapidly in the universe. Now, when we look at some groups that are dynamically quite compact and safe, like the beautiful globular star clusters, these groups of stars, they are suns that are so numerous, so close together, that they really can all right for a long time purely mechanically. On a mechanical basis, this sort of a system is safe for 100 or even 1,000 cosmic years. And the chances of it going to pieces mechanically are slight. But then there come the other changes, the physical ones. And we ask now, what evidence can we get from the evolution of the stars themselves? What can we learn from them about changes taking place in our universe? Here in the diagram, you see our sun in the lower right-hand corner, compared in size to some familiar stars. We know pretty well how our sun behaves and why it behaves the way it does. Our sun is a star that gets its energy from subatomic processes. These processes work roughly in this fashion, that our sun is composed of many gases, among them quite a bit of hydrogen. The hydrogen atoms collide with each other, interact with other atoms, and produce helium atoms. And the one characteristic that one has about these helium atoms is that they will on the whole have a slightly smaller mass than the hydrogen atoms from which they are made. In other words, a little mass is lost while hydrogen is being transformed into helium. As a result of that, a star can burn up approximately a little less than 1% of its total mass and change it into energy. Our sun does that at a very slow and reasonable rate. It can keep on going for 100 cosmic years without any embarrassment. Some of the bigger stars do it a little bit faster. And especially when we come to the real big fellows, the supergiants, then the problem becomes really a serious one. And one begins to find some remarkable things taking place. Take, for example, a star like the one that is pictured there on the left. That is a star like Betelgeuse. A star with a mass somewhat bigger than our own sun, but not too much more, but with a diameter that is so big that Mars could turn in its orbit around the sun inside that particular star. To keep that whole surface burning at a temperature of 3,000 degrees requires an awful lot of atomic energy. The blue-white hot stars, smaller it's true, at the other end of the line, smaller it is true, but exceedingly luminous, have equal problems of where they get their energy. For here we have the problem. Suppose we have the sun right here at this point, one of these luminous giants right up here. If we take the sun as the one star, the luminous giant as the other one, the ratio of the masses of the two is about a factor 1 to 100. What is the ratio of their total luminosities? Well, for the sun, 1 again, the ratio of luminosity for this one is in many cases as high as 100,000 times as great as that of our sun. In other words, the masses 1 to 100, the luminosities 1 to 100,000. In other words, the atomic energy pump in the giants have to pump about 1,000 times as fast as those in the sun. In other words, if the sun can keep it up for 100 cosmic years, This poor star can only keep it up for 1/10 of a cosmic year, and it is on the way out in no time. What we are therefore looking for is especially the properties of the most luminous stars. They are stars that must be subject to very rapid and continuing changes. Now when we look at these stars and look at their changes, we wonder where these stars occur per May. These stars occur especially in regions of the great gas clouds. In other words, it looks as though the gas clouds are slowly condensing in spots and beginning to change into stars. If I had to take a real example of the pre-stellar stage, I would go to this one here. I would take these little dust clouds, globules we call them very frequently in astronomy, little dust clouds that are present in some of these lantern slides and that actually are clouds of dust slowly being condensed by the pressure of radiation and by their own gravity. A cloud like that, present here at a given time, will collapse under its own gravity, will be pushed together by the pressure of radiation. What will happen? The particles will hit the other particles. Those particles will then be scattered. As they're scattered, you will find that you have the molecules forming. The molecules will go to atoms. And finally, as these things speed up and move faster and faster, the atoms will hit each other in their nuclei, and then bang, you have subatomic energy progressing outward, pushing against the star cloud, and a star will have been born. So the process is that of a gradual collapse followed by the formation of the atomic energy. These are the sort of things that have come closest to the pre-stellar stage. How long does it take to form a star in that fashion? Something again of the order of 1 cosmic year. So all the evidence in our galaxy points to the fact that our universe has been going on for a time of the order of a few cosmic years. Let us now begin to turn to the universe of galaxies, the universe of Milky Way systems. Here you will find in these photographs, these hazy spots are not stars out of focus, but they are Milky Way systems like our own, galaxies like our own, floating in space. We know that one of the properties of the universe of galaxies is that they all run away from each other, that they have velocities of expansion, that the universe generally is expanding. We know how fast one is expanding, that is at a certain distance away from us. We therefore know distance, the rate at which it is moving away. We know therefore too how long ago they were all close together. And now we might as well go back to the blackboard. For on the blackboard we found that the age of the Earth was 25 of these cosmic years. That clusters developed mechanically in times of the order of 25, 10, 3, and so cosmic years. We found furthermore that new stars were being formed and were being formed all of the time. That these new stars were being built up out of clouds of gas and clouds of dust. These galaxies, these stars that are present now, they all developed in time ranges of this interval of time. Finally, we turned to the expanding universe, and we found that the galaxies themselves, running away from each other, indicated that they were all close together 25 cosmic years ago. Well, one thing begins to be quite clear, that beginning from the Earth, moving out into the Milky Way system, moving into the universe of galaxies, mechanically and from the physical evolution point of view, that 25 cosmic years is a pretty basic and important interval. And what I would suggest to you is that it is not likely that this is the age of the universe, but that it certainly is quite sure that 25 cosmic years is a very important interval in the development of our universe. What I have done today is to talk in terms of the simplest of classical phenomena. I could have changed this over and told you about other approaches to this problem. I have purposely stayed away from the creation of matter, from the new phenomena that have been suggested from time to time, but that are not yet accepted. In the most conservative fashion, one can say, we have now come to the point where we see evidence for change and development. 25 cosmic years is an important interval. Keep that in mind, and you are safe as far as cosmical development is concerned.
You have surely heard that science advances by applying code, logic, and mathematics to numerical measurements. That the scientist is a man without imagination and without emotions, at least in his laboratory. Now you know for sure that that cannot be said of astronomers, because astronomers, not just one of them, but several astronomers in each leading country and in every decade have been trying to imagine how some recent discovery, such as the release of nuclear energy, could help us understand the riddles of the universe. This speculation has been going on for quite a long time. For the last 200 years, there has been a succession of theories, each one using some new discovery of physics, claiming to explain the formation of the solar system, or of the comets, or more recently of the stars. Today, the latest find in the physics of the particles is held by some as making plausible a continual appearance of new matter in the immensities of space. Such is the scientist's imagination. You can be certain that tomorrow's discoveries in the laboratory, as yet unimagined, will be used in turn for another cosmic theory. And this is how it should be. We cannot experiment in the field of astronomy. We can only observe. And it is therefore much more difficult than, for example, in physics, to check a new hypothesis. Only when a hypothesis is recognized after years of scientific discussion as fitting all or about all the facts of observation, will it have claim to rank with the accepted theories of physics. And this has not happened so far to many astronomical hypotheses. The astronomer is well aware of the necessity for continual criticism, as you have just heard emphasized. And there has never been a shortage of astronomers able to criticize competently the new hypothesis of a colleague. But this has never detracted from the appeal for astronomers and for laymen alike of every new theory on the formation of the universe.
This is National Educational Television.